Hi, everybody. Welcome to our next topic in this idea of fields. We've been talking for the last couple topics together. So we've gone over gravitational fields, we've gone over electric fields a little bit, and today we want to look at a pretty cool application of electric fields, and we also want to kind of bring these idea of fields together. So what we're going to do is we're looking again, as I said, an application of electric fields, but then we're also going to see how do those terms we've been talking about sort of compare to something you're more comfortable with, like gravitational fields. So how can we kind of relate potential and potential energy and potential difference to gravitational fields and things like that? So things that are a little more comfortable, and I think a great way to do it are with these things called parallel plate capacitors. So the first thing, of course, we probably want to ask ourselves is what the heck are these things called parallel plate capacitors? So what a parallel plate capacitor is, um, well, if you want to build one, all you have to do is get two really large plates made of some sort of conducting material. And so often we talk about things that are made of metal because metals, as we know, are great conducting materials. We want to put them close together. And what I mean by when we say close together, we mean that compared to how big they are, the size between them is small. And again, if you're taking calculus, you're okay with these sorts of approximations, or things like small versus big. That we want to talk about that we don't really care about the edge effects, we call them, or how things change towards the edge. So as long as the plates are large compared to how close they are, we can ignore any sort of effects going on at the end. So put them close together, and they want to be parallel to each other. Um, and then what we want to do is we want to charge them oppositely from each other. And so down here, I've got a couple different pictures of what parallel plate capacitors might look like. Um, and so this one down here, this is kind of an idea of connecting up with some batteries here. So you'd plug the negative side of a battery to one parallel plate or one side of the plate, and the positive terminal to another plate. And of course, then if you do that, over here I've got a bit of a schematic diagram. You've got positive charge on one side and negative charge on another. And so this is called a parallel plate capacitor. We call it a capacitor because it has the capacity to store charge. And this is something that's really cool. So capacitors are used all over the place. If you've ever opened up an electronic device, I guarantee you've seen capacitors. They normally look like they don't look like plates actually, because what they do is they take these plates like this, right? But instead of putting them in these big long sheets, what they do is they roll them up into sort of like these cylinders or spirals around each other. And so they look almost like cylinders that are covered in plastic, and they're labeled with the letter F often. Oops, let's get rid of that warning there. They're labeled with this letter F, which actually stands for Farads, named after, again, a famous physicist. We won't worry about what that letter actually stands for or means right now, but you've seen these things. And what they do is they store these huge amounts of charge, and they can release them very quickly. Um, and it's actually kind of neat that there's devices that are being worked on right now that actually might then be used to replace batteries. And the big benefit for why these would be better over batteries for things like cell phones and laptops and tablets is one, they can be much lighter. Two, they don't use any sort of dangerous chemicals to store the charge. So that also means you don't have to worry about the chemicals kind of getting used up, or you get this memory effect. The batteries stop holding a charge. And the other real benefit is that you can charge these things much faster than a chemical reaction can. So you could charge these things very quickly, and the batteries would never need to be replaced because they wouldn't the chemicals wouldn't sort of degrade over time. So I'm a bit of a digression there, but so certainly something kind of cool. Um, but of course, if we have these two oppositely charged plates, hopefully you realize then if there's two opposite charges close together, there's going to be some sort of a field between them. And what we want to do is take a look at what does that electric field look like. And so I'm going to pull out, well, there's the website again of that program I was using the other day. So if you're bored and want to play with it yourself, you can go and do that. Um, but here is this idea of a charged plate. So these two yellow plates, they have opposite charges on each other. Um, and actually, let me stop rotating. Let's turn this off fields for a second. And pardon me 1 second here, guys. All right, sorry, but then never mind. So anyways, the white part again means that the field is very strong, and the green part means the field is weaker. And so what's kind of neat here is you can see that inside or in between these two plates, the field looks pretty uniform, looks pretty straight. You only have these sorts of white pillars that are almost perpendicular to these two plates, and far away from it, the field is actually quite weak. And this goes back to the idea of what we talked about last, or a couple times ago, we talked about these two charges that were opposite, that were some distance apart. As you go further and further away, their separation becomes less important, and so the charge density, or the electric field, dies off. And so if we make these sheets closer and closer together, what you can see is eventually, look how light those green lines are, now they're gone. So there is no sort of electric field outside of the sheets. But if we separate them a little bit, you can see the field gets stronger, but of course we have this nearly uniform field inside. So what do I mean by when I say nearly uniform? I mean that pretty much no matter where you are inside of those plates, the field looks identical. It's always pointing in the same direction, and those lines are pretty evenly spaced, always pointing in the same direction. So that's something pretty useful here. Oops, slow down there. And so we can actually see that sort of effect there, that this is a uniform field inside. And so that's something kind of neat. All right, so let's go back and kind of summarize what we just saw here. So first of all, let's get rid of this weird black line. All right, so anyways, what we can say is far away from the field, the electric field is zero, so that as long as you're far away from these plates, there is no sort of electric field. And if the separation of the plates is small compared to the size of the plates, and again, we can often say that, we're going to make that assumption a lot of the times, we can ignore any sort of edge effects. And what that means is that instead of the field, if we actually looked at, oh, let me get the marker here. Sorry again, guys. If I get the actual parallel plate that kind of looks like this, in reality, the field inside is quite perpendicular to the plates, but as we go out, it kind of bows out. I'm exaggerating it, of course. But as long as we say that the separation is small, we can ignore those sorts of edge effects. And even more important, if we go further away, we can actually say the electric field is zero everywhere outside. So as long as these plates are close, we can say right here, at this point, there is no electric field. And that's going to make our life a lot easier, and it's a great assumption to make, and it's actually quite true so long as the plates are small, or the separation are small compared to their size. And so what else is really, really, really important for us is electric field inside is constant. So no matter where you are, whether here, 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 whether you're right beside this plate, right beside this plate, no matter where you are, the electric field is constant. And so what we get is actually a real life sort of picture of the electric field. So notice, as long as you're kind of near the middle of the plates, that it's a nice perpendicular line and they're pretty uniform compared to an ideal case, so that looks the same. But the edge effects, we get some weird stuff going on. It doesn't quite go off to zero far away, but this is what we'll be dealing with for right now, this ideal case where everything works out perfectly. But again, hopefully you can see that even in the real world, as long as we constrain ourselves to sort of live in this area, it looks pretty darn similar to this area. So even though this is ideal and this is real, they're pretty similar in this case. All right, so let's see if we can actually get an idea of the magnitude of the field inside. So we've got an idea now of what it looks like, but let's get an idea of how big it is. So the way we're going to do this is we're going to look at a test charge. And so our test charge, of course, we're going to give it a symbol, but we're going to ignore it or cancel it out later on. So it doesn't matter what the charge is. So I'm going to give it the symbol Q. So we're going to use the test charge Q, and what we're going to do is we're going to move it from the negative plate, which in this picture is B, and we're going to force it to move all the way to the positive plate A. And of course, you know that are we having a positive test charge here, I actually have to force it. I have to apply a force here because there's an electric force trying to push it backwards. And so I have to do work over it. And so how much force do we have to apply? Well, if we again accept the fact the electric field is constant, it's a constant force, and it's just the electric force. If I want to push something at a constant speed again, all I have to do is match the forces. So the sum of the forces is zero. So it's just the electric force, and I'm going to apply it over a distance of r being, again, the separation of the plates here. So this is the work I have to do to move that plate. And the electric force is just given by the charge, the test charge I've given the letter Q again, times the electric field, because that's our definition of electric field is. Electric field is the force divided by, well, let's try that again. Electric field is the force divided by the, what's going on here? Charge, that's awful. That's better, all right, a little bit. So force divided by charge, then I can just put that in there. But now we're saying again, the work being done is actually being used to store energy as electric potential energy. So this is not just work, this is the change in that charge's or this system's electric potential energy. So I'm going to write it as delta EE over Q. And again, this should look familiar. We call this change in energy per charge, something we talked about last time. We called that potential. That's our definition for potential, which means then the change in voltage or the change in electric potential or the electric potential difference is given by epsilon R, or we can sum it up nicely, even put it in a box for us here, that the electric field inside of a parallel plate capacitor is just given by the voltage or the electric potential difference across the plates divided by their separation. So to go back to my picture here for a second, if I want to change the strength of this field, all I have to do is either put a different size battery inside here, so make this a bigger or smaller battery, or bring this closer or further apart. And doing that is going to then change the electric field inside. And again, the electric field, notice this doesn't actually tell us the direction of the electric field, but we can use our common sense here because the electric field will always point from the positive to the negative, and so we can just work with that there. All right, so let's again do some sort of plug and chug questions here to see if we're getting the idea here. So here is a pretty simple parallel plate capacitor made. So we're hooking up two 9-volt batteries here in series, and they're hooked up to these parallel plates. And I want to know what is the electric field inside. So what is sort of going on inside of here. So let's start with maybe the simple structure. Let's take a look at the picture of these batteries that are set up here. So I have a negative terminal connected to this plate, so that's probably going to be the negative plate here. And I have the positive connected to the negative, and this positive connected here. So again, hopefully you guys remember from grade 9 and grade 11 physics and science that these are batteries connected in series, so we actually are going to add these voltages. So what that means is there's actually a voltage or a potential difference of, or sorry, not 19, 18 volts across this system here because there's 9 from this one and 9 from this one. So these two plates there's a voltage between them of 18 volts. And so again, we want to know the electric field, but if this is the positive, this is the negative, we already know which way the electric field is pointing. The electric field is going to be pointing this way everywhere inside of that. It's going to be pointing towards the negative plate from the positive to the negative. And if we want to get the magnitude of it, well, we just derive the expression down there on the last page. It's the electric field is given by the potential difference across the plates divided by their separation. The only thing to watch out here is watch out for units because this is in centimeters, but this is in volts, which we want it to be anyways. And so I'm getting, when I plunk this in my calculator, 1500, and we could write this as volts per meter, which is certainly a fine unit, but normally we're going to write, of course, a electric field as a force per charge, or then newtons per coulomb, which I will leave to you as an exercise that volts per meter is actually the same as newtons per coulomb. Actually, maybe we'll do that in class next time. We'll see what we get to then. So there's the electric field. So quite a strong one from just two batteries. But just a quick question here then. If I brought these plates closer together, so I actually made this plate kind of go closer to this one, what would happen to the electric field inside of here? Would it go up, would it go down, or would it stay the same? And that's going to be my first question for you on the, I don't know what you want to call it, the survey at the end of this video. So bring this closer together with the electric field in here, go up, go down, or stay the same. All right, so think about that one, come up with an answer, and you're ready to click on one of the options there. All right, the next one. So now let's look at something maybe a little more ridiculous. Where we have your cookie sheets inside of your oven, and they're 10 centimeters apart, and for some reason you want to have an electric field of 10 newtons per coulomb, and so I want to know what voltage do you have to apply to your cookie sheets in order to make that work. So what I'm saying here is I've got one cookie sheet here, one cookie sheet here, and in between them I want to have an electric field. Let's do that maybe in red, um, like this, and so I want the electric field in here to be 10 newtons per coulomb. And as I've drawn it, this would need to be the positive, and this would be the negative. And so the question again is, what voltage, what size battery do I have to apply to make that work? And all we know right now is the cookie sheets are separated by 10 centimeters. All right, so again, what are we going to do? Well, luckily, this is a parallel plate capacitor, so the expression for electric field, is actually quite straightforward. It's just delta V divided by R, or the separation divided by the voltage divided by the separation. Again, I'll leave it to you to verify this, but I'm getting that the voltage is only actually a measly, um, wait, that's not right, is it? Yep, actually, sorry, yep, 1 volt. So it actually only takes 1 volt to do that. So you could do this with a standard AA battery if you wanted an electric field of 10 newtons per coulomb. And so there's that next question there. All right, great. So that's it for the examples here. But I did promise that we'd spend a little bit of time trying to really clarify these ideas of gravitational electric fields. So let's spend a few minutes and do that then. And we have 5 quantities that we need to deal with here. So we have force, we have like this idea of a force field, we have potential energy, potential, and potential difference. And again, they are kind of similar. You don't want to mix them up, so let's go carefully here. We'll start with a description for the easiest one, hopefully, because you've been dealing with force since at least grade 11 physics. What's a force? Well, it's just the force acting between 2 objects. So it's like a push or a pull. Actually, maybe I should write that instead of defining force with force. Let's call it a push or pull. So it's the push or pull acting between 2 objects. All right, and so in gravitational version, what we actually have is just the force of gravity, which is G_mm over r squared. And for electrical, it's just the force of electrical, which is K_q over r squared. All right, so that's again pretty straightforward, I think. The one that's maybe a little bit harder is the idea of a force field, but all this is, it's the region of space where we kind of take away the test charge or the test force, or sorry, no, try that again. We take away one object, the test object, and we only talk about what is one object doing to the region around it. So what is the Earth doing to the space around it? How is it affecting it? So what is the gravity or gravitational field of the Earth? Or we can say I have a giant charge sitting here beside me. What is it doing to the space around it? What would it do to other charges around it? So it's actually force per unit, or force per unit charge, force per unit mass, things like that. And so in gravity, that's the G field, little g, and in electrical, that's the epsilon field. All right, so those two I think are probably okay. The next three is where we kind of maybe lose people a little bit. But potential energy, so this again, we have 2 or more objects and we're going to store some energy because of where they are in space. So there's some sort of force of attraction or repulsion between 2 objects, and we're going to store some energy by putting them somewhere. And so in gravity, it's just the e.g. the gravitational potential energy, so we're again okay with that one, I think. Um, but then we have electrical potential energy, and that's again two charges that are close together, and they're going to be pushing on each other, and so we're storing energy in their system. This is where most people seem to be going off the rails a little bit. What is potential? And just like force field is like the force per unit, potential is like the potential energy per unit. So it's like the energy field almost. It's the energy stored per unit. So it's how much energy we're actually storing um, in one object in the space around it. So if I have one object and I put another test object there, what sort of energy would be stored? So it's kind of a more generalized version of potential energy. And so in electricity, we're talking about V. And then potential difference, that one's pretty straightforward if you know potential, because it's just the difference in potential between 2 locations. So we're either calling that delta V or VAB. But now I think the reason why maybe my analogies break down here is because I can't really think of any sort of common gravitational versions of these things. So that's maybe where this analogy sort of goes off the rails. But we can certainly talk about this, maybe come up with some ideas in class, how these might look like. But that's it out of me for today. So happy watching a video, and I hope everybody understands this, and we'll talk about this kind of stuff in class tomorrow. Have a great night, everybody.